This video is about Bernoulli's equation, which is in a chapter on fluid mechanics. The book I'm using is Young and Freedman's University Physics, and this is the 5th section of chapter 4. Bernoulli's equation. Well, you might remember that there's a pressure equation having to do with the pressure differences between, say, 2 points in a tube where the fluid isn't flowing. And so basically the difference between pressure at point 2 in that tube and point 1, or the pressure at point 1 in that tube, is going to be the negative of the density. That's a rho, not a p, which is, again, mass per volume. The negative density times g, which is the gravitational acceleration constant. Well, it's not constant, 9.8 meters per second squared. And then the difference in height between the 2 points. So pressure 2 minus pressure 1 equals the negative density times g times the difference in height between point 2 and point 1, y2 minus y1. Okay, that's if the fluid is not moving. What if the fluid is moving? Well, if the fluid is moving, then we have Bernoulli's equation. And Bernoulli's equation basically is based upon the fact that kinetic energy and potential energy, as you know, are related in such a way that if the kinetic energy goes up, then the potential energy goes down, and if potential energy goes up, then the kinetic energy goes down. And so basically in this equation, the rho g y1 or the rho g y2 relates to the potential energy of the fluid, and then 1/2 rho v relates to the kinetic energy of the fluid. So a lot of the same terms as the first equation are down here, except we've now added in. So this equation up here effectively is about potential energy, right? The energy due to the difference in height. By moving the fluid, we now include the kinetic energy of the fluid. So the pressure at point 1 plus the potential energy at point 1, which is rho g y1. Again, g is 9.8 meters per second squared. Rho is mass per volume for that fluid. Plus 1/2 rho v squared. That's the kinetic energy at point 1. Rho, the density times the velocity, half of it, squared, velocity squared, is going to equal, the total of the pressure at point 2 plus the potential energy at point 2, which is rho g y2, plus the kinetic energy at point 2, 1/2 rho v squared. And so basically, at any particular point in time, this is going to be a constant for the fluid in question. Okay, that's Bernoulli's equation. To put it into word form, the work done on a unit volume of fluid by its surrounding fluid is going to be equal to the changes, or is it going to be equal to the sum of the changes in kinetic and potential energies per unit volume that occur during the flow. Okay? Some final conditions. So this only applies with an incompressible fluid, and it only applies with an incompressional fluid with a steady flow and no viscosity, that is, no internal friction. And again, the assumption is that the default assumption is the pressure is in pascals, the density is in kilograms per cubic meter, and the speed is in meters per second, and that you're talking about the same kind of pressure. So either absolute pressure throughout or gauge pressure throughout, where gauge pressure is the difference between the absolute pressure and the atmospheric pressure. See an earlier video. You can, of course, change the units, but you have to change them to scale. You have to change them together in an appropriate way. Okay, so this has been a video on Bernoulli's equation that basically says that the pressure plus the potential energy plus the kinetic energy at one point of a flowing fluid at a steady rate is going to equal the pressure plus the potential energy plus the kinetic energy of the fluid at another point. Bernoulli's equation.